Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to talk about series and also summation notation. A series is just the sum of a sequence, and you can either have a finite series, which will only add up the first n elements of a sequence, or an infinite series, which will add up an infinite sequence. Now, we use S sub n to stand for the sum of a finite series of n terms, and we use S sub infinity, or sometimes we use just S to stand for the sum of an infinite series. The notation on the right is what we call sigma notation or summation notation. This symbol is the Greek letter sigma. It's the capital Greek letter sigma, and it's basically equivalent to our S, and S for sum. So this first one means start at I equals 1, go through I equals n, adding a sub I. So it's a1 plus a2 plus dot 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 up to an. So it's a shorthand way to represent the sum rather than listing out all of the terms we're adding. Anyway, we're going to do a few of these, and then we're going to move on to a slightly different type of example using this notation. So we're going to start with evaluating I equals 1 to 5, 3i plus 7. So basically this is saying find the first 5 terms of this sequence and add them. So lots of different ways you can organize this. I'm going to just do this horizontally. I'll do maybe the next one vertically. The first term is 3 times 1 plus 7 plus 3 times 2 plus 7 for the second plus 3 times 3 plus 7 for the third plus 3 times 4 plus 7 for the fourth, and finally 3 times 5 plus 7. And now we just need to simplify each term and add the results. The first term in this sum is 10, 3 plus 7. Then we've got 6 plus 7 or 13, 9 plus 7 or 16. And if you notice, these terms just keep increasing by 3. That's all because of the 3 there. The 7's part of each one, but what goes up as n goes up is 3 times I. Let's see, we've got 19 and 22, and when we add those together, we get 80. So that sum, that series, that finite sum is equal to 80. What's different about the next one? Well, we go from 1 to 6 instead of 1 to 5, so there's going to be 6 terms. And we've got this quadratic expression for the sequence, I squared plus 3i minus 4. By the way, this is not the imaginary number I. We just use I as the index for these types of sums. Sometimes we'll use j or k. I'm going to be consistent and just use I, but you've got to remember that it's not I that's equal to the square root of -1. It's just the natural numbers from 1 to 6. I'm going to do this one vertically. When I is 1, we've got 1 squared plus 3 times 1 minus 4, 2 squared plus 3 times 2 minus 4, 3 squared plus 3 times 3 minus 4. And notice here, it makes it easy for me to see what I'm supposed to change. At each level, I'm increasing the value of I by 1, so the number being squared and the number in the parentheses. 4 squared plus 3 times 4 minus 4, 5 squared plus 3 times 5 minus 4, 6 squared plus 3 times 6 minus 4. So it's easier to set them up that way. Now we'll simplify each one. The top one is 1 plus 3 minus 4, or 0. The next one is 4 plus 6 minus 4, that's 6. Then we've got 9 plus 9 minus 4, that's 14. 16 plus 12 minus 4, that's 24. 25 plus 15 minus 4, that's 36. And 36 plus 18 minus 4, that is 50. Then all we have to do is find the total of that column of numbers. That is 130. So this sum is 130. And we'll do one last one. I'm going to do this one horizontally again because the expression that I'm substituting into is pretty simple. I've got 4 to the I power as I goes from 1 to 8. So that is 4 to the first plus 4 to the second, 4 to the third, and fourth, and fifth, and sixth, and seventh, and eighth. I don't know what 4 to the 8th power is, but by the time I get there, I'm going to have a pretty good idea of what it is because each successive term is just 4 times the previous one. So we've got 4, sorry about that. 4 squared is 16, that's 4 times 4. 4 cubed is 64, that's 16 times 4. 4 to the 4th would be 256. 4 to the 5th is 1024. 4 to the 6th is 4096. Maybe I'm going to be in trouble after all. 4 to the 7th is 16,384. And 4 to the 8th is 65,536. Now, you could, if you're good with spreadsheets, you could use a spreadsheet to do these. You could type the numbers 1 through 8 in the first column, and then in the second column, you could raise 4 to that power, and then you could total that column. That's a pretty efficient way to do it. Let's go ahead and take a look at the scientific calculator to add these up. So I've got 4 to the first plus 4 to the second plus 4 to the third plus 4 to the fourth plus 4 to the fifth plus 4 to the sixth plus 4 to the 7th, plus 4 to the 8th. And there's our sum way over to the right, 87,380. Now, if we look at just those last two terms, which are a little more than 16 and 65,000, that adds up to be 81,000. So almost 82,000. So the other 5,000-ish comes from those first 6 terms, which kind of makes sense. Right. For the other type, this one's going to be a little different. We want to write out the terms of the series and then evaluate them if possible. So in this first one, notice that the lower limit is I equals 6, not 10. And it's just a sub I. So this would be a to the 6th plus a to the 7th plus a to the 8th, plus a to the 9th, a sub 9, sorry, not 9th power. Stuck on that last example, plus a sub 10. For the next one, we're told that x sub I is different for I equals 1, 2, 3, or 4. So the first term is going to be 5 times x sub 1 plus 8. And then we've got 5 times x sub 2 plus 8 plus 5 times x sub 3 plus 8 plus 5 times x sub 4 plus 8. And we were told above what x sub 1, x sub 2, and so on are equal to. We're going to replace x sub 1 by 6, x sub 2 by 10, x sub 3 by 14, and x sub 4 by 18. Now we can do the arithmetic. The first one is 30 plus 8, or 38. Then we've got 50 plus 8, or 58. 5 times 14 is 70, plus 8 is 78. And 5 times 18 is 90, plus 8 is 98. So now we can add those together, and you should get 272 out of that. The last one is kind of similar. We've got f of x sub I. The function is x cubed, and then we're told what x sub 1, 2, and 3 are equal to. Also, we've got a factor. This is read as delta x. Delta is another Greek letter. It looks like a little triangle. It's the Greek letter D, and we use it in advanced mathematics to represent a change, a small change. So let's get started here. This one only goes from 1 through 3. So this is going to be f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x. The function is x cubed. So I'm going to substitute into that function. I'm also going to replace delta x by 4. So we've got x sub 1 cubed times 4 plus x sub 2 cubed times 4 plus x sub 3 cubed times 4. And then we'll add those three pieces together. X sub 1 is 5. So we've got 5 cubed times 4 plus x sub 2 is 9. So 9 cubed times 4. And x sub 3 is 13. So 13 cubed times 4. 5 cubed is 125. 9 cubed is 729. And 13 cubed is, that's off of my radar. Let's check out what that is, and we'll also do the whole sum there as well. First, let's see what 13 to the third power is. That's 2197. And I'm going to show you how to do the whole thing right here in Desmos. So it was 5 cubed times 4 plus 9 cubed times 4 plus 13 cubed times 4. And there we get 12,204. By the way, notice that we're multiplying by 4 in each of those terms. We really could factor that 4 out and just take the sum of the 3 cubes and multiply that by 4. We'll talk about those kind of strategies in the next video, and I'll see you there.